Good morning. This is the lecture on sinusoidal response of RLC circuit. For input, if you provide a sinusoidal for an RLC circuit, how the current expression will be. In the previous lectures, we have dealt with the sinusoidal response for RL and RC separately. And the same procedure is going to follow. And you try to correlate this particular derivation with transient response derived for an RLC circuit. For a DC input, we have derived RLC already in the previous lecture. You try to correlate this lecture with that because the conditions what we are going to get based on damping will be similar. Underdamped, overdamped, and critically damped, and the conditions for that, the roots what we are going to obtain will be of similar nature. Only the thing, only the difference will be the input provided. The input which is provided in the previous lecture case is you should have supplied with a DC input. Now we are going to provide a sinusoidal input. That is why we call it a sinusoidal response. So as usual, we get inside the derivation. We assume that the conditions are initial conditions are 0. So whatever the energy stored in the prior state, that is no energy stored in inductor or capacitor prior. The switch is closed at time t equal to 0 only. So we assume that that is the starting point of the circuit derivation. Okay. So when you apply KVL, Kirchhoff's voltage law, then you can say the applied voltage V will be equal to the voltage across the resistor VR plus the voltage across the inductor plus the voltage across the capacitor. VR plus VL plus VC. So the voltage applied is provided as V sin omega t, where V is the peak voltage, VM. And the voltage across the resistor is R into I of t. The inductor is L into di by dt, and capacitor is 1 by C integral I of t dt. So it is in time domain. Now what we will do, we will go for taking Laplace transform. Laplace transformation எடுத்தோம்னா sin omega t என்ன வரும், omega by s square plus omega square. நான் ஏற்கனவே சொல்லியிருக்கிறேன், இது sin omega t வந்து நம்ம அசியூம் பண்ணி எடுத்துக்கிறோம். sin omega tங்கிறது சைனசாய்டல்ங்கிறதுனால இது cos omega t கூட இருக்கலாம். It may be cos omega t also. அப்ப cos omega t னா இந்த இடத்துல என்ன சேஞ்ச் வரும்? It will be s by s square plus omega square. Instead of omega, you will get a s there. So omega by s square plus omega square ங்கிறது sin omega t. அதே cos omega t ன்னு கொடுத்திருந்தாங்கன்னா you should go for s by s square plus omega square. That is the only change. You kindly derive for that expression separately. So if you take Laplace transform, you are getting this from this expression. Then R into I of s plus s into L into I of s. That initial conditions I of 0 will not be there, and capacitor does not have any initially charged value. So it is going to be 1 by SC into I of s. So now you find I of s as common factor here. So you take I of s common, you will get R plus SL plus 1 by SC. Now take an LCM. What you will get? The LCM, if you take LCM, you will get S into you take LCM, you will get S into RC plus S squared into LC plus 1, the whole divided by S into C. So if you bring this expression to the other side, you take this expression this side. So I can write I of s is equal to V omega divided by S square plus omega square. If you take this to the other side, the reciprocal will be there. So S into C divided by S squared LC plus S into RC plus 1. Now the coefficient of LC, the coefficient of S squared should be 1. So you take this LC outside. So you will have 1 by LC. So S squared plus S into RC by LC, 1 by LC. So this CC gets cancelled. So finally you will get an expression like this from this expression. I of s is equal to V by L into omega s divided by S square plus omega squared, 1 by S square plus R by L into S plus 1 by LC. And for this only you are going to apply partial fractions. To know the character of this particular roots, based on the roots only you will be assuming the partial fraction. The type of partial fractions we take based on the roots only. So it is depending upon two factors here. You can see this equation and this equation. This equation we are already familiar. It is a complex conjugate. It's purely imaginary. S is equal to plus or minus j omega. This is obtained when you equate it to equal to 0. You will get s squared is equal to minus omega squared. That is, I am telling you s squared plus omega squared is equal to 0. If you apply that, you will put s squared is equal to, you bring this side, s squared is equal to minus omega squared. You will get you s is equal to plus or minus omega. It's a complex conjugate term. Okay, when you see this equation, if you equate it to 0, then using that formula, what is that formula? Minus b plus or minus square root of b squared minus 4ac divided by 2a, 4ac divided by 2a. Subject to that, what is a, what is b, what is c here? So a is here is 1, a is equal to 1, and b is equal to r by l, b is equal to r by l, and c is equal to 1 divided by LC, A, B, and C. So when you substitute that, your expression change like that. From that, you bring the relation, take this 2 here. So you will get minus r by 2L. This denominator will be here, available here. You make it as a equation like this. Minus r by 2L plus or minus 1 by 2 square root of r by L the whole square minus 4 by LC. Now if you bring this 2 inside, it should be, okay, if you bring it inside the square root, it will be 1 by 4. Then only if you take this 4 outside, it will be 2. So 1 by 4 into r by L the whole square minus 1 by 4 into 4 by LC. Multiply this. 4 gets cancelled, so 1 by LC. If you bring this 4 inside, it is a square term, so you will get r by 2L the whole square. 2L will be there. Now, based on this square root term, your roots will be different. So we categorize that into three cases, as we have done in the previous RLC, transient response of RLC. The same methodology, the same procedure, and it's a very big derivation which is not required actually to apply that completely and say you just say the condition and formulate the partial fractions type. That is enough, and say what is the type of damping it is going to undergo. அது மட்டும் எழுதுனா போறோம். கம்ப்ளீட் ஈக்குவேஷனையும் நீ சால்வ் பண்ண வேண்டிய அவசியம் இல்லை. யூனிவர்சிட்டி பாயிண்ட் எக்ஸாம் பாயிண்ட் ஆஃப் வியூல பாத்தீங்கன்னா இட் இஸ் நாட் நெசசரி டு டூ தி என்டையர் டெரிவேஷன் பிகாஸ் இட் இஸ் very it's a very long derivation it will be. Okay, so the roots depends upon this factor particularly. So we categorize that into three cases. The first case I am taking, if this r by 2L the whole square is much greater than this 1 by LC, then the roots will be real and different, because let us say if this is 5 and this is 2, then the root will be an integer value, around an integer value only. It will be a real value, and the values whatever you obtain will be of different values, because you will have a number here, you will have another number here. Plus or minus gives you two different roots, two different values, and those values will be real in nature. It will not have any complex terms available. So this condition we call this as overdamped condition. It's a very important 2-mark question also. They may ask you, it's a 2-mark question also. I think I should have notified that in the previous derivation also. These three cases, they may ask you in a 2-mark question. Write the condition for overdamped response for an RLC circuit. They may ask you. If it is that is the case, then you can say r by 2L the whole square is greater than 1 by LC is called as overdamped response. This is the condition. So if you say this is alpha and this is beta, then S will be is equal to alpha plus or minus beta. It's real and different. One will be alpha plus beta, the other will be alpha minus beta. Both alpha and beta will be real numbers. This is the first case. Then how do you apply this if you get I of S is equal to, we know this is complex conjugate S square plus omega square. So AS plus B divided by this term plus D by first factor plus E by second factor. Why I apply this D and D? Because a capacitance C is involved, so you will not get confused with that, with this C coefficient, I mean residue. So I apply D and D. So this is how we have to be based on the values. Whatever we get, your expression will be derived for I of t. You cannot directly write this is that is what I have stricken this also. There is no need to do this. You say this condition, the type of roots, and write the expression. That is enough. Then go to case 2. First case it is greater than 1 by LC. The second case is equal to 1 by LC. Which in the case, if you make this factor equal, then you will get 0 for this. This factor becomes 0 because both are equal. So 1 minus the other will become 0. So only remaining thing is minus r by 2l. So the same root will be repeated. The same root will be repeated. So the roots are real and will be repeated. Let us say if it is alpha plus or minus beta, then you will get minus alpha minus alpha. Or s is equal to alpha, if you get, you will get s minus alpha the whole square, whatever it is. So this is going to be the factor. The roots will be real and repeated. So how to take repeated partial fractions for repeated root? The first factor, residue divided by s plus alpha, second factor divided by s plus alpha the whole square. That is also possible, or you can take this as what I have written. First residue divided by s plus alpha the whole square plus second factor divided by s plus alpha. And this is again already available as it is because it's a complex conjugate term. As plus b by s square plus omega square will remain as it is. And this is called as critically damped response. Critically damped response. It is again a sluggish response. The response, if you draw between t and I of t, if you draw between t and I of t, it will be very sluggish actually. If you say this is your actual value where it has to end, this response will be very sluggish. And this is for critically damped. And if you go for over damped, it will be far, even further sluggish actually. It will take a long time to settle down. And if you go for under damped, which we are going to deal with, your under damped will be looking like this. It will damp around, it will reach that. This is between I of t and t. I of t and t. For a step input, we say. For a sinusoidal also, the type of response what we obtained will be of similar nature. What I am trying to say here is, for critically damped and over damped, the response will be slower, sluggish. The third case now we will see. The third case is going to be this condition, this factor r by 2l the whole square will be less than 1 by LC. That is, for example, this is 2 and this is 5. So you will get minus 3. The square root of any minus term will end with a complex term. So the roots are complex conjugate. It will be minus alpha plus j beta minus alpha minus j beta. So this remains as it is in all the cases, and you can have it like a separate term also, like this d divided by s plus alpha minus j beta. This is one term plus e divided by s plus alpha plus j beta. That is also possible. Otherwise, you can have it, if you multiply these two factors, you will get an expression like this. You can have it as a because this is a complex conjugate term, you can have it as this. So you can have this type of expression or this type of expression, and this is what you call it as underdamped response. So that is how we can categorize that your RLC circuit behaves in a 3 different way based on the value what you obtained for, or the roots what you obtained from that particular expression, which is belonging to this particular expression s squared plus s into r by l s plus 1 by LC. Based on this, the partial fractions type is different and the damping is going to differ, and the expression also will differ. So this is enough for a expression, right? Deriving the expression for an university question paper. So we will stop with this. We will see some more problems related to little complicated problems in the next lecture for RL, RC, RLC circuits. Thank you.